people's experience of the book been so far? Are there any questions that come up, or was everyone able to set up the TF2 environment and import and clone all the files from the repository for this book? So that's what he shows how to do in on the website, I think, on his Git website. Let's see. So should be sharing. I should be sharing the schedule, right? Is everybody seeing that? I think I'm sharing the schedule.
Yeah, I'm seeing it,
yep.
Joseph.
Thank you. Okay. Yeah, so we went through and read chapter 1 last time. We didn't quite finish it, so I know that the time wasn't quite enough to finish it all, but we did have a discussion, and then today we'll just go through some of the. We'll go through. There's not much to do actually, because there's only that one notebook, and it's there's not very much in it. So we'll go through that. We'll talk about something about scikit-learn, something about pandas. Maybe we'll code a little bit in that notebook and extend it a bit. But first, let me just ask: are there any questions about chapter 1 that we didn't discuss last time that you'd like to get into? Any other comments in general? Okay. Right. So let's see. Here's the I switched to the GitHub repo for this class. Does everybody see that now?
Yeah.
Yeah. Okay. So yeah. So here's the notebooks, and it tells you in the README page. You go down here. It tells you how to get all this stuff. Clone it into your Git repo, or clone it onto your machine, and then it tells you how to create and activate an environment for it, and then from there you can immediately start looking at the notebooks. Has everybody been able to do this? Has anybody not been able to do this and has questions about it?
So I didn't follow this, Joseph, but I use Docker containers to create my notebooks. But it still works, but I just went a different route.
Super. So I mean, the main thing is that everybody, as long as you have a way to do it. I mean, you could run it on. You don't have to run it on your own machine. You can do it on Colab too. If you don't have a machine well, I don't think we're making any use, at least in the early part of the class, we're not making use of GPUs or anything. So almost any Windows machine can do this, or maybe I think you should be able to do it on an Apple machine too. But anyway, this basically shows how to do it. You're basically going to copy all of these notebooks. That's what it means. Git clone it into your onto your own machine. This is something. I mean, I guess the overall prerequisite is that you've installed Anaconda on your machine, and so you might want to look into doing that if you haven't. But then from there, I think we went through this last time. You get an Anaconda window, and in that window you can do all of these Unix commands. Let's see. Let me go to that window. Let's see. Share that window. This one. So you should now be seeing an Anaconda prompt. Sorry, a terminal window from Anaconda. Yeah, and oh, it's got a bunch of junk. Well, I've already run Jupyter Notebook. So I went into this. So what I did this morning is I went into, I brought up this window. I activated the environment. Let's see, where's that command? Let's see, I can't go back far enough to see it. The first thing I did was I activated the TF2 environment, which is just conda activate TF2. That's the environment we created last time. And next I went into my directory for hands-on ML2. This is where I cloned all the notebooks, so they're all in here. And once I'm in this notebook directory, then I just write the command Jupyter Notebook, and that immediately brings up a notebook in my browser. So from then on, I lose control of this window because it's all hung up on, it's basically doing the notebook processes in the foreground. So now I don't need this window anymore. So I'll go back and show you the notebook that I'm looking at. Okay, this is, wait, screen one. I should be sharing screen one. Yeah, so now you can see all of my screen one, I think, right? Okay, is everybody seeing this? I'm inside of the GitHub repo, the GitHub repo online for this book. Okay, right. So basically, question? Yeah. So I've cloned this repo on my machine, and now I have access to all of these. So this is what comes up when I do the Jupyter Notebook command. It just brings me up in the directory that I'm in, which is the hands-on ML directory. So now I can see all the notebooks on my machine. And so then the next thing I did was I clicked on this one, the first notebook, which is what we're going to do today. And there it is. So this is just that little code example that we went through. Let's see, now that we have more people, are there any other questions? Are there any questions that anybody wants to ask? We have, let's see, counting. Now we have 35 people here, so that's a good size class. Any questions that anybody wants to ask about the lesson one, about the book, about getting things to run in your environment, about cloning the repo, anything? Don't be afraid to speak up. Okay, so I presume that I can presume then that you've all done this, you've all cloned the repo somewhere and you have access to the notebooks and you can run them whenever you want. Is that a fair assumption? So you can do just what I did, bring up the notebook and run it. So let's look at this notebook. We've already been through it, but I kind of wanted to just take a little bit more time. So let's see. We have, oh yeah, I have already done this. I don't really need to do this because I've already installed scikit-learn. And let me just execute down to where we are. So remember what we're doing is we're importing this database that has to do with life satisfaction versus gross national product, or GDP, gross domestic product for that country. And it's positing maybe a linear relationship between those things, and it's making a plot. It's making a model, and then trying to support that there's a linear relationship. So here's getting the data, and let's see. Oh, importing the data. So this is something that, so here are the things that we're importing. We're importing matplotlib.pyplot. This is very common. Everyone in data science uses some kind of a library to make plots, and one of them is matplotlib. There are lots of newer, fancier libraries like Seaborn, and that's one that comes to mind. There are a number of other libraries that allow you to do sort of really plots with a lot of bells and whistles on them and stuff. But they're all based on matplotlib. Matplotlib has all the commands in it available that you might need to do these things, but to make fancy plots. But some of the newer packages make it easier. So anyway, we'll just stick with matplotlib for now. Numpy, we know, is a way to deal with, you're going to need that if you're doing data science because you have to deal with arrays, matrices, and so on. Pandas is something that people might not be familiar with, especially if you've taken like the deep learning classes and stuff, because we haven't really dealt with tabular data very much in those classes. So Pandas is a special library that is for dealing with, mostly for dealing with tabular data. And that means when I say tabular data, it means like, spreadsheets, that kind of stuff with rows and columns. And then the third thing we're importing is from scikit-learn, we're importing the linear model that allows you to do a linear fit, okay? So we'll talk a little bit more about pandas as we go. So we load the data, and what we're using is this command from Pandas, which allows you to import any CSV file. Read_CSV allows you to import any CSV file. What's a CSV file? It's comma-separated list of values. It's similar to, I mean, Excel format files are similar. So I think that you could use this command to, well, I think if you had an Excel spreadsheet, you'd first have to convert it to a CSV file, and save it as a CSV file, you know, with the .csv extension and all, and then you'd be able to import it with this pandas command. So it's telling you where to look for the file. It's telling you what to use for you know, for thousands. You're supposed to use commas for thousands, and it's doing the same thing. So there's, let's see. So it's importing two data sheets. One is from this. One is, I don't know what these abbreviations are. If I were doing it, I'd write it out so people could understand. So OECD BLI, I don't know what that means, but GDP per capita is pretty clear. That's a good name. So it's importing that file. Now it's displaying these files, and so Pandas imports a file in this thing called a data frame, which is a really nice sort of object for dealing with, holding all of this, the data from a spreadsheet. And so the first thing you can do is to look at the first few lines of this data frame with this .head command. So if you look at this, we can ask for a type. What is the type of this OECD_BLI file? And we'll find out that it's a special type called, let's see, where's, why can't I execute this thing? Oh, there it is, run. Okay, so I run this thing, run this cell, and it shows me that it's a special object called a pandas.core.frame.dataframe. This is basically a pandas data frame. So the object that we imported this, we downloaded this file, and we imported it directly into a pandas data frame. And that's what's so cool about this. You can go from, you know, you can grab something on the web and immediately import it and look at the data in it. So this is one of them, the OECD BLI, and we can see something about what's in it. It's got rows that are countries. It's got something called an indicator. Not sure what all of this is. Measure, value. It's got a bunch of columns that we don't really need to know too much about right now. Maybe this is the column that they're looking at, which is the measure of life satisfaction or something. Anyway, we can look at the other one as well and see that it's just what it says it is. It's got rows that are countries. It's in units of dollars, and it's showing gross domestic product. I'm not sure what units these are. Maybe they're billions of dollars. It should say, but it doesn't. Anyway, this must be, it might be, I don't know, maybe it's millions of dollars. I don't know. Anyway, so then he goes through this thing to prepare the data for our model. And usually you want to have your data in an array X, and your labels for, you know, for a supervised problem, you want your data in an array called X, capital X, and your labels or targets in an array called small y. This is just a convention that people use. All right, so let's see, np.c. I'm not sure what this np.c is. NP is NumPy, but C. Has anybody seen this command before? np.c underscore? No?
Yeah, it's you can actually in a separate cell do the np underscore c question mark, but it's basically a way, if I recall, of showing what's the way to put it? Column. I think it's best if you just do it, and then
So this is, if you see a command that you don't understand, you can get its documentation this way by putting 2 question marks and running that cell. So what does it do? It translates slice objects to concatenation along the second axis. I'm not quite sure what that is, but
basically puts us as columns rather than rows, as Raquel says.
okay. So
it's
if
column format versus the row format, row dominant. So
it's basically switching
columns.
them, or okay.
No, it sticks it as columns versus sticking them underneath each other, sticking them to the right or left of, if you can imagine that.
Mm-hmm.
You don't concatenate along the row, so you don't make the table longer, you make it wider.
The transpose, is it?
It's how you stitch it, meaning where does the new column show up there.
Well, let's have a look at, let's run this cell first, and then we'll see what these objects look like.
Yeah, it's how, I think flu is a good word that Alex is using. It's how the new columns are glued to the old ones. They are glued along the second axis.
Yeah, if we see, like, the C underscore must be related to columns, right? So it's like grabbing everything and doing one column, only one column. compared to R, when we see in translate slice objects on something, it's like R should be rows and C should be columns, I guess. So it's like gluing everything into a variable.
Well, let's look at country stats first, just to see what it looks like. So country stats is, there was this, I think there's this code underneath that takes as input these 2 data frames and prepares them and prepares this object to be used in the modeling. So let's first of all look at what that looks like. First we'll see what type it is. And so it's also a data frame. So that means we can display it. We can just go country underscore stats dot head. I put head because if you put dot head, it's just going to show you the first 5 lines, and otherwise it'll flood your screen with data. So you can look at it. It's just a small thing. It's basically so it's basically taken the 2 pandas data frames, and from them it's made one with the first column being the GDP per capita and the second column being life satisfaction. That's exactly what we want to try to model. We want to, and the hypothesis is that they're linearly related, that life satisfaction is proportional to how much money the country has. So yeah, so now I'm still not, so X must have extracted X must have extracted the first column. I just don't understand why it's using this. This is a rabbit hole that we can dive down and understand, look at the definition of this function and understand it. But I don't think I want to spend the time to do that right now. The point is that X is just extracting the first column, and Y is just extracting the second column. And we can see that by I think it's small enough so that we can actually let it show us the whole thing. And there it is. Yeah, I think it's 29 elements. It's just a column vector with 29 elements, one for each country. And these are the these numbers are the GDP per capita. So that must be, maybe that's in thousands. Now maybe that is in dollars actually. So GDP means gross domestic product. That means, and per capita means the share of that per person. So what it basically says is that each person has access to this many dollars on average per year. So in Afghanistan, the first country is $9,000 a year. Down to the last country, the average person has access to roughly $56,000 a year. So that's our data. And let's see, we can show the whole thing since it's small. We now know that it's small, so let's just show the whole thing. There it is. Oh, it's Russia. Russia was the first country, $10,000 per day, and United States has roughly 56,000. sorry, $10,000 per year, roughly, or 9,000, yeah, rounded to $10,000 per year for Russians, and their life satisfaction is 6. And Americans have roughly $56,000 a year, and their life satisfaction is a bit higher. But the question is, you know, is their life satisfaction higher because they have more money, or what? So we don't know that. And so I guess that's what they're trying to do here, is to model it. They're saying, what happens if we make a linear model? So next, okay, so we have x. X is a vector, y is a vector. Now we're just going to plot it. So this is the function. This is matplotlib then, right? But actually, this is pandas. Pandas knows how to use matplotlib, and so it can use, if you go pandas data frame dot plot, then it knows that it's going to use matplotlib to give you the plot. So pandas has its internal ability to do plots. So you tell it what kind of plot you want, which is a scatter plot in this case. A scatter plot is just, you know, having 2 dimensions and plotting them as points, plotting them as 2-dimensional points. X GDP, it tells you which one you want for X and which one you want for Y. So X is GDP per capita. This is the X, the label that you want for X. GDP per capita. The label you want for Y is life satisfaction. So these 2 things are just telling you the labels you want. And then it does the grid. And then plt.grid. PLT, remember, is matplotlib's pyplot package. And .grid says just superimpose a grid on top so you can actually make more sense of these dots, where the dots lie. And then show. So now we've got the plot. So what we're doing, this is kind of what's called exploratory data analysis. We're just looking at the data, plotting it, looking at the data frames, seeing what numbers we have to deal with. That's exploratory data analysis, and in this case, it's very simple. Let me pause here and see if there are any questions or questions you want to bring up from last time. Okay. Speak up, anyone? Okay. Let me look at the chat then and see what we've got on the chat. So let's see.
Yeah.
Yeah.
Just a side note again, Joseph, on the C_. I'm talking to people here and they're saying like np.c_ is just a way to concat values along the column axis, like but with slicing syntax. It's like it kind of means nothing. It's like,
I mean, but I mean, if you take the data frame and you take the column, you already have that. That's why I'm not sure why.
Yeah, I think there's nothing like special within it. It's like just scikit-learn that defines the trailing underscore to denote computed values. So maybe something like Numpy has something to do with it.
Yeah, I don't know. I mean, because what I was thinking is, and we can try this. I was just thinking, I've never seen that command before, so it's always nice to learn something new. But why couldn't we just do x equals, you know, just give me the column, and then, right, and then y is the other column.
Yeah, if you see, I did that in the on my machine, and it's kind of messy on the chat, but I think you can see that like it just scrapped the numbers. So
you just get the same result then, right?
Oh, you put them to Numpy arrays. This way you get only a Panda series.
Oh yeah, this is a Panda series, but then it's easy to extract what's in the Panda series by doing this.
Yep.
Yeah, I think using the Panda column like straight, we would have the same results, I guess.
Oh, you don't really need to convert it to NumPy? Let's try it. Let's try it. Okay.
Yeah, I guess let's try.
So one way is just to extract the values, but someone is saying that we don't need to do that. So why do something extra if we don't need to? So suppose we just extracted the columns as pandas, and what happens when you extract a column from a data frame is it's called a series. So the first thing we can do is I'm going to do this outside. Sorry, I'm going to do this outside of this just so we can see something. Search. So what if I do this? And then what if I ask myself, what is going on here? Type, what is X? What is a type of X? And it'll tell me that X is a, oh, it's interesting. It extracted it as, oh, that's because.
No, you haven't run it yet.
I haven't run it yet. Yeah, oh, let's do that. So let's see what it did. It gives me it says that it's a pandas object called a series, and that's basically a column of a data frame. So these are the types of objects that you deal with in pandas. You deal with data frames, and you deal with columns of data frames, which are series. So, and Y is also a series, so as you'll see. Right, so there it is. So let's see what happens if now we're gonna run this without these extra commands here, just see if it works. And we get an error. So what does it say? It says none of country are in the columns. Okay, why did it do that? None of country are in the columns. Format missing, key error.
I think it's
country
the
stats.
way that prepare country stats is written.
Mm-hmm. But oh, okay.
Definition is.
But prepare country stats is run before we run the X and Y. So now I'm a little bit confused. Let me see. Oh no. Okay, hold on. X and Y. Maybe I did something to country stats. Prepare country stats. So prepare country stats doesn't see X and Y, so it shouldn't be throwing up an error here. Let me try something.
Yeah, maybe put country stats also in the same cell as X and Y. Yeah, put the line in the same, just above that X and Y.
Yeah. Although it's just I'm just going to run it all by itself. It's giving an error. Why is it giving an error? OECD BLI. Well, let me start again then from the top. This is quick, so it doesn't waste a lot of time. Import. We don't need to run that. We can just execute this again. Now, I should. So this is that function prepare country stats. Now I should be able to. Sorry. I should be able to run this thing. Country stats equals prepare country stats. That's giving me the same here. OECD BLI. I'll run this again. So it's reading in the data again. See what it looks like. Oh, did we change it? We must have changed things. Let's see. It didn't look like that before. See this one. Okay, pay attention to what it looks like now, which is what it looked like at first, and then, oh, it's the same. That's fine. All right, now why can't I do this? Now it works. Okay, for some reason, I had to run that code again. I'm not sure why, but now let's try this. It's throwing up again. Okay, well, this is something we could worry about later. Let me try one more thing. I'm going to function again. I'm going to remake the BLI, these two files, and then I'm going to go into that cell without having run it before. So let's see. So I do the preparing. Aha, okay, that worked. Nope, but it's throwing up something else. Now it throws up and says, value error, expected a 2D array, but got a 1D array instead. What is it? Where's that happening? Numeric model fit. Okay, let's see. It didn't like okay, so it did the plot, but it didn't do the fit. It made the model too, I guess, but it didn't It didn't
I
like
think
the
the-
input to the model.
I think the model dot fit is
It
looking for a
wants
numpy.
it wants NumPy, right?
Yeah,
So
model.fit is
let's
supposed to receive an array-like object, and
okay.
we're
So let's
passing the series.
right. So let's just take. I think there's a way to. So X, remember, is a pandas is a series. So what is the? Is it two? Let's see. There's a command you can do that converts it to a NumPy array. The easiest way to do that. Does anybody remember?
I think
Maybe
if you
2
scroll down to
NP.
the error, if you scroll to
Pardon?
the error, the reshape error, it tells you how you can reshape it.
It doesn't need to be reshaped. It's
2
already.
NumPy.
All I need to
2.5.
do is 2 NumPy or something like that, or maybe.
Yeah,
Yes,
no.
2 underscore numpy.
Sorry.
2 underscore NumPy.
2 underscore NumPy. 2 underscore
Yeah, NumPy.
NumPy. Okay, so let's replace X with X converted to NumPy. And let's replace Y the same way. Y dot 2 underscore NumPy, like that, right? So now we should be able to run this last part.
Joseph, I think if you put X dot values,
Yeah, that's another way to do it. That's another way to do it, right?
and it should be a NumPy array with that.
Yeah, I think that's another way to do it. So remember, so what's what the gentleman said is that there's another way that alternatively you could just take, I believe this would work, X dot values would work as well. Or no, there's no I think there's no paren. Yeah, Y dot values. That's another way to convert a core data, a pandas series type into a NumPy array. But anyway, we've handled it here. Now we should be able to execute this without any. Oops. That's still didn't.
Yeah,
like
now I
it,
get it. Goten put in the chat that np._c is just to convert X and Y to D NumPy arrays. So the second dimension would be 1. And if you use that, Joseph, like
you need that for let's see.
Actually, it's the reverse. It's the second dimension which it is concatenating along, and the first dimension is 1 in this case. That's why you need the np_c. So Gautam is right, but it's 1 comma that. That's what I was just about. So and all scikit-learn inputs.
Is it making a column? Is it making a column of ones? Is that what it's doing?
No, it's concatenating along the column dimension. So you get 1 and then like whatever or when I say 1, I'm simplifying to be in the simple case. In the other case, it's just that it needs, as Gautam said, a 2D array to be supplied, and it generates the second dimension while concatenating the values along the column dimension, not along the first axis. That's why you see the statement being made that it is concatenation along the second axis, but it generates 2D, as Gautam points out. And all sklearn fits require 2 dimensions at least, if I recall correctly.
Yeah, that's right. So it's, but Y doesn't have to be converted that way. Why is it doing that with Y as well? I mean, Y is just
Y also needs the same format. That
I think Y needs to be 2D as well. And when we use X.2 underscore NumPy, we're converting it to a 1D array only.
Joseph, because in the general case, X could have a number of columns and even Y could be a 2-dimensional matrix, right? So just to handle those cases as well, it always expects 2D X and 2D Y. Okay,
let's make sure, let's just check that here. So I've got linear regression in scikit-learn, that's what we're using. And here is an example. But before we do that, let's go back to, let's see. Let's go back to where they actually discuss linear regression. I think I have that over here. So this is linear regression, and it'll tell you what needs to be the inputs and what needs to be the outputs. Let's see. It should be telling us what. Oh, let's see. Maybe we'll go back to the beginning. That's linear models, ordinary least squares, X and Y. Let's see. so these are the inputs, the data and the target values. So that would be the x and the y. But and more generally, x is usually multidimensional, not just one-dimensional. So that's called the design matrix. So usually x is a two-dimensional matrix. And I don't know why y should have more than one dimensions, because generally, if you're just doing ordinary least squares regression, or ordinary regression, you're mapping multi-dimensions to one dimension. So I'm not sure why y should have to have two dimensions in it.
What if we use np.c_ for x and leave y as it is and try it?
Yeah, but I just don't like this. I don't understand. I really say I don't understand this np. I don't understand this c_ command, and I'm trying to figure out a way to bypass it because it's just not clear. I've heard people talk about what it does, but it's not clear to me what it does. If anybody can explain it really in a concise way, what it does, if they know, I would be glad to hear it.
Yeah, people are telling me here that there is numpy.stat to replace all of these weird things. So numpy.stat should do the same.
Okay, I think I've messed this notebook up enough. Let me find out where we were again. There we go. This is there. These are the weird commands that. What is it actually doing? Is it trying to make x into a two-dimensional array with two copies of the column or of the country?
It's introducing an additional axis.
Just adding
and the
an
axis,
empty.
Sorry, go ahead.
Sorry, go ahead. Go ahead, sir.
So it introduces an additional axis, and the axis can be either a row or a column, the additional axis. And that varies depending on whether it is np.r or np.c. Now, I don't want to comment on which one is which because I get confused, but that's what it does. It introduces a 1, everything else. So, for example, as Gautam says, it's a reshape of, and if you're familiar with the reshape command and then a -1, that means it throws everything that isn't the or everything in a multidimensional tensor into the the -1 look. That's the first axis, and then retains a second axis.
Okay,
so
I think I understand. I think there's an easier way to do it. Okay, so if I do this, then I convert to a NumPy array, and let me just make sure of that. So before we do that, before we use that weird command. Let's make sure that we got our NumPy arrays out, type of x and type of y. So we're expecting this to give us NumPy arrays, right? So let's see if it does. Oops, what did I do wrong? NumPy array is no object to num. Okay, so to NumPy is not a real command. So that's one problem. Let's go back to the values. I know why it didn't work because we had already converted it. That's right.
Correct.
That's right. Sorry about that. Let's go back.
Now you just have to reshape it.
Yeah, I just have to grab x and y again. Now it's gonna throw up on me because I have to. Let's see if this will work. Sorry, this is a rabbit hole that I didn't anticipate going down. So let's see if this works. Yeah. So now we're back to this is x and y as Pandas series. Now I can convert them to NumPy and verify that they are. So it says it doesn't have an attribute. But this is weird because let me see what we got out of x and y then. What is x?
These are arrays right now. Joseph.
Oh, they're arrays. Okay, fine. Yeah. But I thought they were series. I thought we had verified that they were series. Oh, that's because we've done this conversion. Let me just see what it gave us. X.shape. So it did add. Okay. So before it did that, it was just the shape would have been 29 comma, and it made sure to add to make it into a column, I guess.
Yeah,
I think that's all this does.
Could you use counter stats like without the np.c score underscore and then check the shape?
Yeah, let's do that. I think I might have to go back and make country stats though, but we'll see. What have I done wrong here? There. Yeah. So now we can check the shape. Okay. So this is without the weird C underscore command that I've never seen before. Yeah. See, that's what I thought. So all we're doing is we're adding. So it's now considered as it's just a vector and it's not a matrix, an array. So we need to make it into an array, a column. We need to make it into a two-dimensional array that is a column. And this is just a vector. This is one of the pain in the necks about Python. And Y is shaped the same way. So there's another way to do this, I think. Let's see, I'm going to do this for a second. X, isn't there a way to do this like none something, wait, where you want the new dimension, you put none. I think this might do the same thing. Oops, I want the shape.
Or you can use the Numpy reshape function.
Yeah.
Yep.
Yeah. So there's two ways of doing it. It's several ways of doing the same thing. If you have a vector like this and you want to make it into a one-dimensional array that has that is a column array, you put none where you want the new dimension to be inserted, and then you get it like that. So now we can rewrite this stuff without the weird commands, right? So we'll just say, we'll comment out, we'll just say x equals, I'm sorry, I don't want to erase this, I just want to comment it out. Sorry about this, we're going to get there. So I did that, I'm going to get x and y as country stats, and then I'm going to replace them with, I'm going to add the extra dimension like we want. So I'm going to go x equals x of none, right? That's how you make it into a two-dimensional array. And oops, I had never seen this before. This method of doing things. People have mentioned that you can also do it by resize. So that's another way to do it. You can resize the 29 comma object into a 29 comma 1 object by using resize. But this is another way to do it.
Reshape as well.
Reshape, thank you, reshape, yeah. And the first time I saw this was from Jeremy, actually, this technique of adding an extra dimension by using none. So anyway, I like this better. So now we should be able to plot the thing and model it. And what's the last thing is, oh, let me just run this thing, make sure it runs. Oh. Country, it gives me the same error about this country thing. I don't understand that error. Let me just chop this off and put it in another frame, in another cell, so we can figure out what's going on. Okay, first let me make sure this runs. Nope. There's something funny about this country stats thing. You have to run it again from the beginning, so let me do that. Sorry about this. This is really taking longer than I thought, but so that's where we get the data out of country stats. That's here. So now we should be able to run this. Nope. I'm not sure why it's throwing up like that. Prepare country. Oh, I have to remake OECD BLI. That's what I forgot to do. Go back to the, this is the thing I have to do. Remake those things. Then come back down here and run it. There. Now it did what I want. So now I should be able to do this part. Now, I'm not sure why I had to do that. I had to remake this thing, OECD BLI and GDP per capita. I had to remake that. Otherwise, it gave me this weird error. Okay, now I should be able to plot and model. And then the last thing that we tried to do was to fit the model. We don't need this anymore. Print type X. Train the model. Yeah. So you're seeing all the sausage being made here. I'm doing all this stuff that trying to get something to work. This is how it is. This is the command that I'm looking for. So this is the command that train the model with. Now I've already got, oh, I want to put it here. It's right under, this is where it was in the original notebook, right? So we've prepared the data, that's this part. Now we visualize the data. We've done that. And next thing we do, so this is kind of like the process we're going to be learning for how to, how to do machine learning on a data set. And then the third thing is to figure out what kind of model you want and then build the model. So we've visualized the data. So step one was preparing the data. That's what we did here. And remember, we got rid of this weird command here because nobody ever uses that I know of. Visualize the data, which is just plotting it, plotting life satisfaction versus GDP. Next is to build a model. And now this part should work. The training the model should now work. Yeah, so we have the model, and the last thing he did was just one simple thing to look at the data for Cyprus. But I think we can do a little more. So starting with our model, let's go back to the example. So this is how you learn from this sklearn, like the scikit-learn, right? It's got a really great documentation. So the first thing I did was look up linear models, and then I find that there is an example there. So I was browsing around here, I found that there's a linear regression example. So now I can just go here and steal code to make it do what I want it to do, right? I'd like to see that little line. I'd like to see what the model looks like. So let's see how we can do that. So let's watch what they do. Here's another example. They're just importing this diabetes data set. They're using the same model we're doing. They're just, instead of calling it model, they're calling it REGR for regression. And they're doing the fit just like we did. So this is where we are. Now, what we didn't do yet is do the fitting for the whole data set. So let's steal some of this code and modify it for our purposes. That's what is great about the scikit-learn library. You can just steal code and modify it to do what you want to do. So we've already got the fitted model. I'm going to put all this junk down here and modify it as I would like. What I'm trying to do is I'm trying to get the predictions out of the model. So let me do this. My model is called model, not regression. And what I want is, I'll just call it YPRED, right? Model, well, yeah, model. My model is called model instead of REGR, so I'm just replacing that. Now, if I want the error, I get my predictions versus the data. In this case, it's just called Y. So Y is the original data, and YPRED is the predictions of my model. Oh, and I don't want diabetes X test. I want just X. That's my data set. So I'm modifying this code for my use. And coefficient of determination, R2 score. So I can get the R2 score from diabetes Y test. I forgot what diabetes Y pred. It's just test and pred. So this is just Y and Y pred, I think. So it's the R2. It's the R2 score, which tells you how good of a fit you've got. We've already seen the outputs.
So Joseph,
Yes, sir.
this is like you're going to be predicting on the training set itself, right?
That's right. That's exactly right. Yeah. So we're just remaking the same scatter plot that we already did, but now we're going to superimpose on it the prediction line. So X and Y. Did I do that right? Let's see. Y pred. Somewhere here I should be plotting Y pred.
That second line where your cursor is, that's Y pred. X Y pred.
X Y pred. Yeah. Yeah. Okay. Let's see what this is going to do. Okay. Error, mean squared error is not defined. Okay. So we'll define it. Make our own function. I don't know. So we're going to define a function that will produce the mean squared error between two inputs. And you know what that is? It's just, oops.
The mean squared error is under metrics on scikit-learn. So I believe you can just...
So maybe I don't have to redefine it myself. Okay, so let's do this. So what would you suggest? From scikit-learn import metrics, or?
Yes, yeah, exactly. Import metrics.
Joseph, I think is
It should be sklearn, right?
sklearn, thank you. So from sklearn, so I'm going to import this metrics package that has the mean squared error function, so I don't have to make it, but it's easy enough to make it.
Yeah.
Anyway, yeah, so is this it?
Yeah, if you want to do it that way, add dot mean squared error.
Metrics dot mean squared error. Metrics dot mean squared error as mean squared error.
Yeah,
will this work?
This should work.
I would suggest, like, from sklearn dot metrics import mean square error, so you don't need to.
Okay.
Yeah, you can do that.
That's good. Okay, from sklearn dot metrics import mean squared error. I like that better. Yeah.
Yep. Import.
There we go, like that, right?
Yeah.
So now we have thank you. Now we have access to this function, and we should be able to run this thing. Okay. So we do the same thing. From metrics import R2 score.
So you can just like comma mean squared error comma R2 score.
Okay. Thank you. I didn't know that. You can import multiple things with a comma. Thank you. So now we should be able, now we have this function that we need, and there it is. So now we've made a plot just like that. But we should, you know, what I don't like about this plot is it doesn't have any numbers on it. So anyway, but anyway, so we can see the model that we made this. We built this linear model.
Joseph.
Yes.
So if you'd like to see the numbers, you can comment like pot.xticks and pot.yticks.
Yeah, that's weird. I don't know why. You know, I don't even know why these things are in there, because normally a plot will give you, will show you the numbers. Yeah, there we go. So here's the GDP per capita, and here's the life satisfaction, and it looks like a very, you know, it looks like a very good trend. But later on, I think they're going to continue with this data set in in chapter 2, but I'm not sure. Later on, we're going to see that even though this looks like a linear trend, it's not really. It's not really. It's not really that definitive because they don't have they don't have enough countries in here yet. Anyway, so let's look at our. Let's look at what we have. So the coefficients in this case, I think we're fitting only one coefficient, which is the slope, I believe. And the slope is very small, 10 to the minus 5. Does that look right? Yeah, maybe it is. And the mean squared error is 0.18. Yeah.
Yeah, the coefficient is small because you have dollars on the x-axis.
That's right. That's right. Okay.
Thousands of dollars.
That's right. Okay. Mean squared error is 0.18 and that would be in life satisfaction units, I guess. So that looks, not too bad. It's like this. It's like about 1/5 of the way, or about 2/5 of the way between these tick marks. That's the error, and that looks about right. Yeah, so you've got a sort of a tight fit. What else can we learn from this? Later on, I think I remember he discusses this, that if you include more countries, you find that this is more that the trend goes away. It's really more like a flat. It's really indistinguishable from a flat trend. But I forgot where I saw that in the book.
I have a question.
Yes, sir.
Shouldn't we have two coefficients, one for the y-intercept?
Yeah, I'm not sure. I think that when we called the model, it by default only fitted one. So let's see if we can change linear regression to make it fit both. Let's see. Yeah, because when we look at coefficients, it only gave us one back. Same thing here. So it's ordinary.
The other one is in the intercept. The intercept, I think, is there on its own.
Oh, it comes. Let's see.
One is coefficient, another is slope.
Oh, okay. So what do we? Let's look at model then. Let's see what we can get out of model. We should be able to get everything out of this thing. So let's see, fit intercept and intercept. Oh, we should be able to get intercept, and why don't we have a slope? Oh, coef. Let's see something. Insert cell below. Is that what we got here? Yeah, there's that thing.
And you can try model.intercept underscore.
Yeah. Model.intercept. This is not okay. So this is kind of like a little confusing because if you're doing linear regression, you usually think of a slope. Well, but then if it's, see, this is a simple case of one parameter linear regression. There's only one independent parameter, but in the most general case, X would be not just a one-dimensional array, would be a two-dimensional array with a number of columns for the different features. And so then I guess you'd ask for you'd talk about the coefficients as being the individual coefficients corresponding to each feature. So that makes sense. So Gautham's question is a good one. He's basically saying, where's the other parameter? And we did fit another parameter. We fit the intercept, and this is how to get it. Okay. And if we look at the plot, the intercept would be if you extend this line, the blue line, if you extend it all the way, where would it cross the y-axis? And you can sort of eyeball it and say, well, it would be somewhere around 5.2 or 5.25. And what we find is that, oh, it says 4.8. Maybe I eyeballed it wrong. If we eyeball it, oh, because this isn't 0. That's the thing. That's the reason why. So if the point is, if it where it crosses the y-axis, that's where the intercept is. But notice here, this is 10,000, 20,000. This is something like, 7,000. It's not the 0. So you'd have to extend it all the way back, here or something. And that's why it would be below, it would be 4.8. Okay. Let me go and look at the group chat and see if are there any questions that are in the chat that I know that we've been dealing with some of these questions as we go, but does anybody want to call attention to any of the entries in chat?
Hey, Joseph, quickly, you said something about the mean square error of being between 5.5 and 6. I didn't get that point.
Oh,
when you...
I'm sorry. The mean squared error was calculated as 0.18, I think.
Yeah, a little down.
Yeah. So we
about
found
that plot.
Yeah, but this one is the intercept. Is that the one you're asking about?
No. If you go up to the plot, just a little scroll up a bit.
This is the slope, not the intercept. Up to the plot.
Yeah, right here. So
okay.
Here.
Yeah. So your question is about the intercept, right?
No, my question is about the mean square error. You said while you were saying something about MSE 0.18, you said something about it between 5.5 and 6. I didn't get that point.
Okay, I don't think I said that, or if I said it, I didn't mean it. When you eyeball this, you can sort of see that the standard deviation of these points around this line is somewhere is some fraction of a unit, like maybe 0.2 or something.
Oh, okay, that's what I said. Okay.
Yeah,
okay,
and then when you calculate it out, it's 1.8. Usually, if you take the biggest one, that's usually the largest deviation from the line is usually somewhere around 3 standard deviations. So that's just an eyeball rule. But yeah, when you calculate the standard deviation, it comes out to be something like 0.2, and that's a measure of scatter of these points about the line, about the fitted line. Okay, and you could do you could pretty this thing up by making it have a grid. You could put a label. We labeled it above. It doesn't have a label here. I could just grab the labels that I already made. This plot was made with Pandas, so it had a way of making the labels, but I can do the same thing with Matplotlib. So I can just go, and this would be PLT, that's the plot object. X label is the label for the x-axis. And all it wants is a string, and do the same thing, PLT dot y label. And again, it wants a string. So this is how you set labels for your plots using Matplotlib. And it doesn't matter whether you're using double quotes or single quotes. I usually use single quotes. Like that. And so now I can make this plot with a label. I even could put a title on it if I wanted to. Oops.
There's a typo for the X label.
Oh yeah, X label. Thank you. Yeah, if I wanted to, I could put a title, plt.title, life satisfaction versus GDP. See, so this is how you can customize your plots, make them look nice, because nobody wants to see a plot that just has a bunch of, oops, sorry. I put the grid on it after I showed it, so that's a no-no. PLT.show shows the plot. Before I show the plot, I want to put the grid on it. So I'll fix that. So this is what a plot should look like if you're going to present your data. You have to have nice labels on the x-axis and the y-axis. You usually have a title. You always want the numbers. Nobody wants to see a plot with no numbers on it, like the original one that they had that I stole from the scikit-learn site, right? So, okay, I guess we're at the end of an hour and a half. If I had more material, I would push all the way till. What time did we start? We started at 10. No, we're not at an hour and a half. We're only at an hour. Yeah, so we don't have to push this class all the way to 2 hours. I'm anticipating that some of the classes will have so much material to get through that we will want to use the whole 2 hours. But at this point, we could stop and answer any questions that came up. I see some good suggestions for how to do the reshaping instead of using this. That's good. Yeah, I don't know where he gets this. This is the weirdest NumPy command I've ever seen. Okay. Is there anything, I haven't looked at all the chat. Is there anything from the chat that would be good to talk about?
So just a side note on the on that comment, Joseph.
Yes.
These guys that I was talking about, they are NumPy core developers, and they find it weird as well. So it's not just you. Don't worry.
That's good to know. Yeah, it's much more straightforward to do it the way we did it, or using the what was it, the reshape command right here.
The only interesting part is the way how he did it is much faster when you time it.
Is that right? Okay, maybe that's the reason for that.
You know, and yeah, it is, which is interesting.
Okay, that's a good point. A good point. I did not know that. Did you know that before, or did you try it actually?
No, I just tried it out right now when we did it and compared them. Yeah.
And also very early on, before the frameworks, I saw a lot of np.c and np.r in NumPy related code. It's only after emergence of PyTorch, TensorFlow, and other things that I think the reshape and other commands which simplified it have become much more common. I encountered the R's and C's a lot in very early data science related, NumPy related notebooks.
Huh. But if there is something special about these commands because they're fast, then at least they're not as stupid as I thought they were. So thanks for that insight. I guess we do have some time. There's maybe one more thing we might want to try. Remember we talked about regularization? Let's see if we can, instead of just doing a straightforward linear fit like this, we can do a regularization. By the way, before we go on to do that, now we have all the predictions. We can, let's see, we can actually look at any data. We can actually look at any prediction we want. Ypred, let's see if I look at that. Let's see, I could do, okay, so we know that Ypred it corresponds to our list of countries. And so now this basically predicts the life satisfaction for every country in our database, for all 29 countries. Give me a country and I can tell you, by indexing in here, I can figure out what its life satisfaction is. That's what our model gets us. And what this command is doing is it's plotting all of the predictions and connecting them by a solid line. We could, let's see, if we wanted to, we could plot them as just points. Let's see, how would I do that? I would do this. Suppose I wanted to plot them as blue points. I could go blue dot. Let's see, color. I think this would work. Let's see if we can. Yeah. So now I'm basically plotting all the points, all the things as separate points. You see. So, and each one of these points corresponds to the GDP that corresponds to its country, right? But by omitting the marker, this is a marker. By omitting the marker, it just says, just give me connect the dots and show me the whole line, right? So that's just the two different ways. So I could do both of these things. I could plot the points as circles to make it bigger, and then I could plot the line going through them. I could plot the points as red circles, and then I could plot the blue line going through. But let me put the blue line first so that I'll be able to see better. Let's see. So let's see what that does. Oh, I forgot to put I made it plot red circles, but then I told it the color should be blue, so get rid of that. there. So now I've got this is the fitted line. The blue is the fitted line, and the red are the data points. The fitted values for the data points. Does that make sense to everybody? Okay. So now I thought what we would do in the remaining, I'm not going to use up the whole hour, but just to do something interesting, let's try to do regularization. Go to scikit-learn, look at our linear models, backwards to linear. Okay, now regression, I want regression. Let's see, I think, yeah.
Joseph, just a question. Are you sure you want to do regularization here? Because usually it's meant for a situation where you have many, many independent variables.
Yeah, but it's just interesting to try it out, right?
Sure.
Yeah,
okay.
So we know about regularization now, so let's see if we can try it out. Let's see, so ridge regression is what we want. Linear model ridge. So instead of using linear model, we'll use linear model ridge, and we'll give it this alpha. I think that controls the regularization, how much regularization we want. We will just do that. So going back here, where we fit the model, we can fit, we can make another model, model 2 equals linear model, let's see, sklearn dot linear model dot ridge with alpha equals 5. Okay, so this is ordinary. So the first model we used was basically plain vanilla least squares. Now we're going to do, okay. So this is ordinary least squares, the first one. Ordinary least squares. Now we're going to do ridge regression, which has basically, if you remember, ridge regression is this is basically the linear model with the addition of the sum of the squares of the features. So it's that's called ridge regression, but what it is basically implementing regularization. Okay, and now we can fit it. The syntax of sklearn, once you get used to it, is pretty simple. You can fit you can fit your data, you can fit your model just by giving it the input. First you build the model. This is just the general model, the prescription for doing least squares with regularization. And now we apply this model to our particular data set. That's what this line does. So let's just run this again. And now we can do this whole thing. We'll just add ypred 2 equals model 2. And the only thing we might want to do now, let me go back to hiding the data points, just the line, just the fitted line. And let's see what the second line is going to be. So this is going to be the line fitted by the ridge regression model. And I'm going to make it red so that we can compare it. So let's have a look at that. Oh, where's my blue line? I guess it didn't matter. So somebody was right. He said that, I think he said it wasn't going to do anything. Let's see. It looks like if I get rid of this, the original model is exactly the same. Okay. Trying to think about why that should be. So in this case, ridge regression didn't get us anything. Didn't get us anywhere. Maybe, as the gentleman said, because we're only dealing with one-dimensional data.
The ridge regression, the alpha is regularization.
Yeah, we could try different values, right?
Yeah.
Let's see.
You need to
Maybe
change
that parameter is not.
Oh, sorry.
Okay, so let's try make it more regularization. So let's make it. I don't know what the range of this parameter is. Is it from 0 to 1?
Yeah, 0 to 1.
Okay, well, let's give it more regularization. So we'll make it like 0.75. How's that? Try that, see if we get anything different. I still have both plots. Let's see, put both plots on there. See what happens. Still nothing. So regularization didn't do anything here. Model ridge alpha. I'm not sure why that should be. I think I was expecting that it was going to. I was expecting we were going to get some kind of a slightly different result.
So like Sriram is saying on chat, maybe we can compare the R2 scores instead of trying to look at the lines, the plots.
Okay, let's do that. So let's see, print R2 score of ypred2. So we'll just R2 coefficient of determination. Oh, we'll just add another line for right. Oh, exactly the same. And we can try to get the error as well. And okay, so do that. Oh, the same error too. So something is going on here. The regularization isn't doing anything for us, and it'd be good to figure out why.
Yeah, Joseph, I think it's like what the earlier person was saying. You just have one x variable, right? X is not a matrix, right?
Yeah.
Yeah. So the way I think about it is like so. For example, there's another related one called lasso, right? And they both have the same effect. Like if you had only one x, like although I never tried this, but
okay.
Yeah,
let's try. You think we should try lasso then?
But I think it might be the same.
You think?
Yeah. You
Okay.
can
Well,
try.
let's do it as an exercise, right? There's two ways of doing. There's two ways that they usually teach of doing regularization. Ridge regression is adding an extra term for the sum of the squares of the fitted parameters. That's ridge regression. But lasso regression is when you add the sum of the squares. I'm sorry, instead of adding the sum of the squares of the parameters, you add the sum of their absolute values. Just slightly different. We can try that and see how that goes. Let's see. I see multitask. There's simple lasso. Okay. So, and what does it look like? It just looks like this. And again, it has a regularization parameter. Usually use a small one here. So let's try that. Model 3. So there's that, model 3. And then, we can do model 3 fit. Model 3 fit. Okay. Now we run that again. And this is I didn't put comments here. Usually I'd like to put comments, but I'm just trying to do this as a quick one-off thing. So, so the next thing we can do is the predictions from the third model. Model 3.predict. And now all we have to do is add a third line. Let's see, plot. What color should we make the third line? Green. Green for lasso. Oh, and it comes out right on top of the first two lines. So apparently that's not giving us anything different.
Yeah.
It needs a little thought to figure out why.
Yeah, for lasso regression, I think if a feature turns out to be useless, it would just change it to 0. So
Yes.
which is obviously not good here. And
Yeah,
as for
that's
Ridge,
true,
I
since
think,
we only have one feature.
yeah. And as for Ridge, I think it is the model is better off keeping the same slope, because that will provide the same the least loss, because this feature is actually a good predictor of the y. So it's better off keeping the same slope than trying to reduce the slope, and even reducing the slope would actually increase the loss than if it had the same slope. So I think that's why it did not give any changes.
Yeah, the main reason for regularization is when you have more parameters than what you need to model, and it's, as we discussed in a different context, the bias and the variance trade-off in this case, by using at least the ridge, which is the just lowering the weights. There's only one parameter that you're evaluating. So if you reduce the weight, your bias is just going to increase. So the lowest bias is when whatever the weight you've gathered by doing it without regularization is the one you want.
So we have two parameters, right? And so the extra term that we'd be adding with ridge regression would be the sum of the squares of the slope and the intercept. Whereas the extra term that we'd be adding for the lasso regression is, well, it's alpha times that thing. And the extra term for the lasso regression would be alpha times the sum of the absolute value of the slope plus the absolute value of the intercept, right?
Yes, you're right. But the point is, if you have many more parameters than what you would like or what you need, quote unquote, to fit the data that you have, then those are the circumstances in which the regularization helps, because the regularization says don't increase the weights to the parameters, or it introduces, in the ridge case, a barrier saying don't increase it unless your increase is going to be better than even the penalty that I impose on you. And therefore, it tends, when ridge regression is used, to go with small weights. And therefore generalizes better. In this case, again, we're just using two parameters to fit a line, which a line requires. If we had a model, if you used, like you said in a different context, Joseph, you use, let's say, a 3 or 4 parameter model, rather than a linear regression. Let's say you used a sinusoid or something else, then regularization, if it tries to fit, then you have many more parameters than the 2 parameters you need to actually fit the line.
Now that's a good suggestion. We could try fitting it to a cubic model and see what, or we could try fitting it to a quadratic model and then see if regularization helps there.
Yeah. So in that case, you may see a difference, but in this case, it's just 2, and if it gives 2 parameters and 2 within the constraint of 2 parameters, this is the best fit. It's not going to do anything if you regularize.
It's interesting though to see.
Yeah, I agree with that.
Yeah. Sorry. Go ahead. Could you again say what you agreed with? Sorry, I missed that. So I just want to verify that. Well, there is something going on here, right? This is the original coefficients. Ridge regression gives you gives you the exact same coefficient, exactly the same out to however many 8 decimal places. But lasso regression is slightly different. So lasso regression is doing something. Maybe if we change make it stronger, we'll get even a bigger difference. I don't know. It might be worth trying this just for a one-off thing. All we have to do is change the lasso coefficient, make it big. Let's make it 0.75. See if that changes things. Well, it didn't have as it changed it, but not by a whole lot. So.
By the way, I don't think the lasso coefficient has a limit of 1. You can keep it as big as
you can go one. You can go even higher. Huh? Okay, well let's try giving it a really big lasso coefficient, like 3 or something.
I think Ben has mentioned also that you can try like 1,000 value or something.
Try a what?
Try 1,000 plus value for the lasso alpha.
Oh, okay. Let's try that. Because we are making some small changes in the you know, in the fitted slopes. So let's try that.
I wonder would the difference be in relation to the defaults for the parameters. So if you look at the default for tall,
look at that. We're getting an effect. So yeah, go ahead. Sorry, Adrian.
Yeah, no, I was just going to say, so in the ridge linear model, the default precision for tall is e to the -3, and for lasso it's e to the -4.
Mm-hmm.
I'm wondering, would that be impacting the resultant coefficients, because you're not overriding those values, I think, when you call the function.
No,
right?
that's right. The tolerance is, you know, the two numbers you mentioned are 10 to the -3, 10 to the -4. That's for judging when the fit is converged, I guess. So I'm not sure how those would relate to here. But we did notice that when we follow the person's suggestion to set the alpha even larger, we got a big result. So now let's make it really large and see what happens. So yeah, you're telling it to not prefer the flat model over the slope model by making the coefficient really big. So we can go somewhere in between 10,000. In other words, it's the lasso. Oh, it's still flat. Okay, so basically, as somebody mentioned, I forget who it was, but somebody mentioned that lasso tends to eliminate parameters if it can. And so when you give it a really large parameter, it basically decided we don't need the slope. We'll just use the intercept.
Can you
That's
try large coefficient for ridge?
Yeah. Okay. Great. Well, let me back off just a moment to make it small enough so that it doesn't eliminate the slope. And then we'll try your suggestion about ridge. So we had 1,000, and we know that 1,000 didn't eliminate the slope. So maybe make it 3,000. See what happens. Yeah. So you can see it's lasso regression says it makes it more conservative about getting a high slope. It doesn't like to have large values of relatively large values of parameters. So now it's saying, well, be careful, don't give me too large of a slope. And so it's keeping the slope smaller than it would normally be. So that's interesting. Now let's follow. I think it was Gautam suggested. Let's try the same thing with ridge regression. So I presume that alpha can be bigger than 1.
No, it's
No?
1. Yeah,
Just
1 is.
make it closer to 1. Okay. So what do you think? Like 0.9? Sorry, Gautam?
I think it can be as big as you want.
Really? Okay. Well,
No.
let's try it. Let's try 10. See if it works.
Wow.
Okay. Okay. Well, it didn't complain, but it didn't change. Let's see. It didn't change the coefficient. So apparently we need a very large value to make it change.
Changed a bit.
Changed a bit? Okay. Let's make it 100.
You can compare the R-square value to see which one is performing better.
Oh, okay. There's the coefficients, and we print out I thought we printed out the R-squared value somewhere.
Not for the ridge in the
last
okay. I guess.
Okay, let's somehow there it is. Print. Yeah, the last one. I forgot to put that extra line in for the third model. Measure ridge regression. All right, lasso regression. Okay, now we can get the R squared. Coefficient of determination. Wait a minute, something's wrong. Why? Oh, there it is, 0.73. Yeah, so coefficient of determination is getting worse. Well, for lasso, it's worse. But for these two ridge, for the ordinary model versus ridge, it's the same. But as Gautam pointed out, it's changing a tiny bit. So we just need to make it even bigger. We have 3,000. Let's make it 10,000. Oh.
No, that's the
Wait, I
lasso
made
you
the wrong
changed.
one. Yeah, I did the wrong one. Sorry. Yeah. Back to 3,000. That's what we had before. Make this 1,000. See what happens. This is a ridge regression. See if we get any appreciable change. Not yet, but let's see. Oh, it is changing a tiny bit in the last few decimal points. So we just got to keep going higher.
Also, it doesn't make intuitive sense because ridge actually has squared of the weight. So I would have assumed that
Yeah, that's
that
right.
should
That's right.
reduce faster than lasso.
Yeah.
I'm seeing the help here. So Ridge says like linear least squared with L2 regularization.
L2, yeah.
So alpha would be correspondent to 1 divided by 2 seeing other linear models. So what if we make alpha like smaller than 1, like 0.01 in the regularization case?
Well, I think that'll just say don't use very much regularization, because small values of alpha mean don't apply. Like if alpha were 0, that would mean don't apply any regularization. So if we make alpha equal to like like 0.01, that's gonna. We already know that small values of alpha don't do anything. There must be a reason.
The alpha is 1 by default also, so it doesn't make sense to.
Come again?
Yeah, say that again. I thought alpha was 0.5 by default.
No, it's 1.
Oh, it's 1.
Yeah.
Okay, so if you put in 1, well, I don't. Yeah. Apparently, it takes values anywhere between 0 and infinity. So, yeah. So there's a reason we're probably wasting too many CPU cycles thinking about this. There's probably a good theoretical reason why ridge regression doesn't do us any good. But at least we did demonstrate that that lasso regression does have an effect. It makes the slope lower. Anyway, so yeah, we'll see more of this as we go on. There's certainly going to be a chapter where we discuss this and where we discuss different regularization methods in great detail. So this is good enough for now. So I'm good to stop here if there are no other questions or discussion matters.
So I think, yeah, one more thing. So I think it does do regularization by default. So if alpha is 1, there is some regularization done by default. So you have to make it explicitly 0 to do no regularization.
Yeah, yeah. For this one, for these regression for these
ridge
regression.
For ridge and for lasso, if you set the alpha equal to 0, it will go back to ordinary least squares, right?
Yeah.
But if you give it a positive value, then it will apply the regularization. Yeah.
This is the linear model dot
right.
ridge. I confused it with the normal one. Yeah.
Okay. Yeah. You can get back the normal. Sorry. Go ahead.
Lasso equals 0 would be a ordinary least squares.
Exactly. If you set the alpha parameter to 0, then you get back the ordinary least squares model for either of these lasso or ridge. The alpha parameter basically controls how much regularization you want, and if you set it equal to 0, it basically says don't do any regularization. And what's that? That's the ordinary least squares model.
Yeah, I put both equations on the chat. So yeah, that's why you're right on that, Joseph. So if we zero that, we zero the regularization part, and we go back to a ordinary least squares problem.
Yeah, great. I see that. So anybody who's made comments on the chat, I'm gonna save the chat so everybody can, so that it'll be preserved. We didn't I know that a lot of people had comments on the chat that we didn't get to discuss. I'd encourage you, if you have a comment that you think is worth discussion, just speak up too, just say something and we can discuss it. So I'm sorry for anyone who had comments on the chat that we didn't get to. Any other comments or questions? Okay, well then, we'll see you next time. I think our schedule says that Salim will be doing the end-to-end, he'll start us on the end-to-end machine learning project chapter on Wednesday, I think. Let's see. Oh, yeah, the schedule is off. We're done with chapter 1. Today is June 14th. That's because we didn't need an extra session for the orientation, right? So I'll fix the schedule, but on Wednesday we'll start the chapter 2. Okay. Thank you all for being here, and we'll see you on Wednesday then for chapter 2.